Le Chatelier was a French scientist who did a lot of work in mines. And while he was looking at the mines, he came up with this idea how equilibria could be changed by things like changes to temperature, volume, pressure, concentration, and all different kind of things. So Le Chatelier's principle states, when a chemical system at equilibrium is disturbed, it returns to equilibrium by counteracting the disturbance. And I know that's as clear as mud, so I'll give you some examples. But anyway, at equilibrium, Q and K are the same, and so if they're disturbed, the Q will just change back to the K as necessary, and I'll talk about that more here in a little bit. A chemical equilibrium system can be disturbed by either adding a reactant or product, and if you add a reactant or product, the reaction's going to shift to the other side of the reaction, all right? So adding a product or adding a reactant will essentially shift that reaction to the opposite side, and that's kind of a trip. On the other hand, if you remove a reactant or product, according to Le Chatelier's principle, removing reactants and products, the equilibrium will shift to the side that you remove things from. So let me show you here what this means. This is the N2O4 going to NO2 reaction. Again, the N2O4 is colorless and the NO2 is brown. Now, this is an endothermic reaction. And in an endothermic reaction, you can actually add heat as a reactant to show that it's there. If this was exothermic, if that delta H value was negative, you could have written plus heat next to the NO2. But not in this case, all right? The NO2 is the product and the N2O4 is the reactant. So K equals NO2 squared divided by N2O4. But notice the change to the equilibrium constants. At 0 Celsius, freezing of water, it's 0.00077. And then at 298, which is roughly room temperature, 0.0059. So in this case, as you go from 273 to 298, you're essentially adding heat, all right? And in that last blurb on the last slide, it says as you add something, the reaction will shift to the product side. So going from 273 to 298, that's like adding heat. You're making the reaction warmer. And in this case, then, you're going to have more NO2 and less N2O4. And in the equilibrium expression, that means more NO2 and less N2O4. And that means your K value, it'll be larger at the warmer temperature than it is at the lower temperature. And that's what we see. So 0.0059 means more NO2 than N2O4, but 0.00077 means more N2O4 than NO2. So because this reaction is endothermic and we're increasing the heat, we're going from 273 to 298, the reaction's going to try and adjust to the change. So that means more NO2 will be made, less N2O4 will be around, K is going to get bigger. So K changes with temperature big time. All reactions are exo or endothermic. All experience a change in K as you change the temperature. But in this case, with this endothermic reaction, you're going to end up with a more favored K as the temperature increases.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
Notice how the flask got a lot darker, a lot more brown as you took away the ice. So you're heating it up. The reaction's going to shift to the side opposite the heat. You're going to see more NO2, more brown, than you do the colorless N2O4. So the flask certainly gets more brown as you heat it up, all right? That's because the heat is being added. The reaction gets away from what you add. It's going to make more product, and product has NO2, the brown stuff. So this reaction has chlorine reacting with fluorine to make two ClF3s, two chlorine trifluorides. And notice that heat is a product. Heat as a product means that it's exothermic. That means your delta H is going to be negative. So think about that in the back of your mind. But anyway, here we're raising the temperature. Now, raising the temperature is like adding heat. And as you add something, the reaction tries to get away from what you add. It goes in the opposite direction. So by raising the temperature, you're adding heat, making it warmer. And this reaction is going to try and get away from the heat. It's going to try and cool itself down, if you will. So if you're adding a product, the reaction is going to shift to the reactant side, to the left. So we would expect there to be more chlorine and fluorine as you raise the temperature instead of ClF3. And that's because this is an exothermic reaction. Endothermic would be the opposite then, if what would happen. But that's why it's so important to pay attention to the sign of delta H. If your chemical reaction involves all gases, it's very important to think about the relative numbers of gas molecules on each side. So for the N2O4 going to NO2, you can see you've got one molecule of N2O4 going to two molecules of NO2. So there's more gas on the product side than there is on the reactant side. And why that's important, because volume and pressure will affect how concentrated these things will get. So for example, if you have a bigger volume, like you change it to a bigger flask, or less pressure, there's going to be more room to move around, and the equilibrium will shift to the side with more molecules. So in this case, it would shift to the side of NO2. On the other hand, if you decrease the pressure, the volume of the system, or you increase the pressure, now all of a sudden the molecules are feeling more trapped, and they'll tend to form the single or the fewer sides of molecules. So a smaller volume, higher pressure, you will end up with less molecules. They want to be as low impact as possible, if you will. So that's why it's going to shift in this case to the N2O4.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
So again, focus on the number of molecules on both sides. So we have 1 N2O4 and 2 NO2s. So if you have smaller volume, the more molecule side will tend to shift to the less molecule side. So smaller volume and higher pressure, for that matter, will shift to the fewer molecules, i.e. the N2O4. On the other hand, if you have more volume or you decrease the pressure, which is possible with a vacuum, it'll shift to the side with more molecules, because now you've got more moving room. They want to be kind of moving around. So in this case, you'd shift to the side with more molecules, the NO2. In this reaction, which is the chlorine reacting with fluorine to make two ClF3s and it's exothermic, let's think about what would happen to equilibrium by decreasing the volume, all right? And if you see a problem like this, decreasing volume or pressure, increasing volume or pressure, you have to think about the relative number of moles of just gas on both sides. So in this reaction, you have chlorine and 3 fluorines on the reactant side. That's 4 moles of gas. And on the product side, you have 2 moles of ClF3. So it's 4 moles on the left-hand side versus 2 moles on the right-hand side. So as you decrease the volume, the atoms don't have as much room to move around. And 4 moles will take up a lot more space than 2 moles on the product side. So as you decrease the volume, it should shift to the side with fewer molecules. And in this case, that's going to be the ClF3. The product. So we would say this is a shift to the right, a shift to the side with fewer molecules. Now, if you increase the volume, it would be the opposite. But here we're decreasing the volume, not as much room to move around. It's going to shift to the side where you don't have to worry about volume quite as much, the side with the fewer molecules. Concentration changes will also affect the position of reactants and products, but concentration changes will not affect the value of K. It affects the position of equilibrium, but it doesn't affect the actual value of K. And to demonstrate this, I'm going to use this water U-tube. This isn't the YouTube with little cat videos and stuff. This is a water-based system. So imagine on the left-hand side with the reactants there, we're going to have quite a few reactants going to some products. And right now the water is at equilibrium. Gravity will affect how the water, reactant, and product volumes are affected. And to make sense of this, we're going to use what's called the Haber-Fish reaction. This is how they made ammonia at during World War I, kept Germany in the war longer, which isn't always the best. But anyway, this is a very product-favored equilibrium, 3.5 times 10 to the 8th at room temperature. But more importantly, notice how there are 4 moles of reactant. You've got 1 mole of N2 and 3 moles of H2, 4 moles total, making 2 moles NH3. And if you use your imagination there in the water U-tube, the reactant side looks about twice as big as the product side. So that's kind of the idea here, and we'll see then how the equilibrium is affected as we change different values of concentration.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
Remembering that a true water tube would be affected by gravity, if you start adding water to the left side, our reactant side, the initial volume will squish down the water. You'll end up with more products on the other side. The final equilibrium is at a higher spot, but it still is equilibrium. And this same process applies in chemistry. So if you add extra N2 or H2, the equilibrium will shift to the right. Adding reactants will move the reaction to the product side. So here's kind of a punchline of a lot of Le Chatelier's principle. Adding a reactant moves it to the product side. And we're going to see that adding a product moves it to the reactant side. Same idea. And even better yet, adding something will move the equilibrium to the opposite side. So in this reaction, once again, chlorine plus fluorine making 2 chlorine trifluorides. It says predict the effect on adding chlorine. Well, adding chlorine is adding a reactant, and adding something means the reaction is going to shift to the other side. Since chlorine is a reactant, and that's what we're adding, this is going to shift to the product side. It's going to have a shift to the right. So adding something, the reaction will shift to the opposite side. Adding a reactant will move it to a shift to the product side, or a shift right.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
If you remove the water from our U-tube, then the gravity on the quote-unquote product side will be greater than the gravity on the other side, and it'll push the U-tube down, so you have a new equilibrium position. And this analogy is very close to what's happening if you remove a reactant from a chemical system. Because if you remove a nitrogen or hydrogen, whatever, the reaction's going to shift by trying to have some of the product reform reactant. So this is going to be a shift to the left. So like before when we said that you add a chemical, the reaction shifts to the opposite side. Well, if you remove a chemical, the reaction will shift to the side that you're removing the chemical from. So if you remove nitrogen, a reactant, it's going to move to the left, move to the reactant side, which is pretty cool. Here's the same question. We want to predict the effect on equilibrium by removing F2, by removing a reactant. Well, if you remove something, the reaction will shift to the side you're removing. And since F2 is a reactant, that's going to shift to the left. So removing F2 will have a shift to the left, a shift to the reactant side.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
So like we saw earlier, when we added a reactant, the reaction shifted to the opposite side. We made more products. Well, here, we're adding more product. And adding product will shift it to the left-hand side. You'll make more reactants. So this would be a shift to the left. And again, all these things can be understood if you just remember that adding something, you're going to shift the reaction to the opposite side of what you're adding. So if you add a product, it's going to shift to the reactant side. If you add a reactant, it's going to shift to the product side. Same question, but a little bit different perturbation. Same reaction. What's the effect upon adding chlorine trifluoride, adding a product? Well, adding a product means you're going to shift to the opposite side. We're adding a product, it's going to shift to the reactant side. That would be a shift to the left. So adding something, it'll move to the opposite side of what you're adding.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
So like we talked about earlier, when we removed a reactant, the equilibrium shifted to the side of what we removed, so it moved to the reactants. Well, here we're removing a product, NH3, and the reaction will also shift to the side of what we're removing. So you remove a product, the equilibrium will shift to the right. It'll be a shift to the product side. So let's look at a more practical example here. We've got a system of equilibrium. It's between the butane isobutane thing we looked at earlier. And remember, for this reaction, because isobutane is the product and butane is the reactant, you need to have isobutane over butane equal 2.50. And initially, that's what we have. Initially, we have an iso of 1.25 molar and a butane of 0.50. So 1.25 divided by 0.50 equals 2.50. We're at equilibrium. However, we're going to spike our system with 1.50 molar butane. Now, butane is a reactant. So the question comes then, what are the new iso and butane concentrations? Well, first of all, let's think about just in Le Chatelier's principle what's happening. We're adding a reactant, and reaction will shift to the side of opposite away from what you're adding. So since butane is a reactant, this should be a shift to the product. So what's going to happen is our product, the isobutane, that 1.25 number should get a lot bigger here, and it'll do it at the expense of our new butane. But let's see how we would calculate this.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
This is a problem where you could absolutely calculate Q first to see if by any chance, after adding the extra 1.50 molar butane, are you really at equilibrium or not? And of course, you'd find out you aren't. But anyway, that will allow you then to make a prediction as to the direction of the shift you're going to have to make to get the reaction back to equilibrium, because that 2.50 number has to be followed at this temperature, no question. So let's calculate Q. Q is products over reactants. Now in this case, the product is still 1.25, but the reactants will be the initial 0.50 plus 1.50. So when you do the math here, Q comes out to be 0.625. Remember, K is 2.50, so Q is certainly less than K. We're not at equilibrium. And when Q is less than K, that means you're going to have a shift to the right. The Q value wants to be more like the K value, 0.625 wants to be more like K. And that can only happen if that number gets bigger. And numbers will get bigger if you have a bigger numerator at the top or smaller denominator at the bottom. So this is going to be a shift to the right, absolutely. We can use an ICE table to help us out here. So initially, you have 0.50 plus 1.50 molar butane, and isobutane is 1.25. Now, the Q versus K thing allowed us to calculate that the product will be going up. That's a shift to the right. So it's easy to see how that would be a plus K, a plus X X right there for isobutane. But you can't get something from nothing. That plus X has to come from the butane. Butane would be minus X. Both butane and isobutane are 1-to-1 ratios. So at equilibrium, you'll have 2 minus X for the butane. You'll have 1.25 plus X for the isobutane. And you can let that all equal the equilibrium constant 2.5. Okay, so there's our ice table from before. The equilibrium constant's 2.50. So 2.50 equals the isobutane over butane. So 2.50 equals 1.25 plus X divided by 2 minus X. So we got to get all the X's on one side. We'll start by multiplying both sides by 2 minus X. So that gets rid of the 2 minus X in the denominator on the right. We then have 2.50 times 2 minus X equals 1.25 plus X. From this point, you could use distributive property, 2.5 times 2, and also minus X times 2.50. When you do that, you get 5 minus 2.50X, so 2.5 times 2 is 5, and 2.50 times minus X is minus 2.50X, and that still equals 1.25 plus X. So again, get all the X's on one side. I would add 2.50 to both sides to get the X's on the right. I would then subtract 1.25 from both sides to get all the numbers on the left. If you do that, 3.75 equals 3.50X. Divide both sides by 3.50. X 1.07 moles per liter. So, at the new equilibrium position then, the butane is 2.00 minus X, 2.00 minus 1.07, and that comes out to be 0.93. The isobutane will be 1.25 plus X, so 1.25 plus 1.07 gives you 2.32. So we ended up once again with more isobutane than butane, which is good because our equilibrium constant K is greater than 1. It's going to be product favored. But it has shifted the reaction towards the products, towards the isobutane. So adding a bunch of butane just ended up at the long run making more isobutane, which is kind of cool to know. So here's an overview of Le Chatelier's principle. If you change the temperature, you change the value of K, all right? Changing the temperature changes the value of K. And you can also result in changes associated with pressure, volume, concentrations, all kinds of stuff can happen if you change temperature. But it will actually change the value of K. Now, if you add or take away a reactant or product, you don't change the value of K. You'll adjust the positions of them, but you won't actually change the number. And remember, the important part here is that adding something, it moves the reaction to the opposite side. But if you take away something, the equilibrium shifts to the side that you took it away from. And that's basically knocks that out. You can have a catalyst. We haven't talked about it, but catalysts just make the reaction come to equilibrium quicker. K itself is not changed. Catalysts are usually more talked about in the kinetics chapter, but if you see anything about it, it doesn't affect the position left, right, or anything like that. It just makes it achieve equilibrium faster, which is kind of cool too. In the last chapter, we talked about Gibbs free energy, and Gibbs free energy and equilibrium constants are certainly related to each other. So if you have a delta G and you want to find K, or you have a K and you want to find delta G, you can use this expression. Delta G equals minus RT natural log of K. R here is the so-called energy R. It's the 8.3145 joules per mole Kelvin. And you want to make sure that you use that. Temperature, of course, will be Kelvin, and this works for all the equilibrium constants you can think of. This is just a sculpture called Equilibrium, supposedly. I don't know. I thought it was kind of cool and artistic, but it really doesn't have anything to do with it. But anyway, if you are at standard states, if you're using that little superscript degree symbol, delta G 0 superscript equals minus RT natural log of K. However, if you aren't at standard states, then you can use delta G, the delta G at non-standard states, equals delta G at standard states plus RT natural log of Q. So if you have some kind of weird set of conditions, Q will help you go from one to the other. Honestly, the one we're going to use the most is delta G equals minus RT natural log of K. And any of the equilibrium constants we're going to talk about, and there will be quite a few, you can turn that back into a delta G using this expression, which is a pretty cool thing. So let's say you wanted to find the equilibrium constant K for this reaction, dinitrogen tetroxide going to nitrogen dioxide, knowing that the delta G, the Gibbs free energy value under standard conditions, is a positive 4.80 kilojoules. All right, no problem. So what we'll do is you'll use minus RT natural log of K equals delta G. But there are a couple of things I want to tune you into. First of all, notice that the value of R is joules per mole Kelvin. Mole isn't showing, but that's what's there. And the delta G values, like delta H, are usually in kilojoules. So one thing you want to make sure you do is you turn your kilojoules into joules first. So that way you're using a delta G with joules and an R value in joules. You can also convert both of them to kilojoules. It doesn't really matter, but you don't want to mix joules and kilojoules together. So anyway, delta G positive 4,800 joules equals 8.3145 times the Kelvin temperature, 298 Kelvin, times the natural log of K. So we'll solve here for natural log of K. That equals minus 1.94. If you anti-log it, which means take e to the x to it, so e to the minus 1.94, the equilibrium constant here is calculated to be 0.14. And at first it might be hard to make sense if these values are sensical or not. However, remember that delta G values greater than 0 are the ones that are non-spontaneous. And non-spontaneous is just another word for reactant favored. And in this chapter, we've seen that K values less than 1 are reactant favored. So if you have a positive delta G, you should have a K that's less than 1. Likewise, if you have a delta G which is spontaneous, i.e. it's less than 0, it's a negative number, then that means you should have a product favored K, a K that's greater than 1. So delta G's that are positive go with K's that are less than 1. Delta G's which are negative goes with K's that are greater than 1. And that does sometimes help to figure out if your answers make sense or not. So here we have a question. At 452.2 Kelvin, an equilibrium constant's found to be 0.444. Let's calculate delta G. Okay, so delta G equals minus RT natural log of K. So minus R, 8.3145, times T, the Kelvin temperature, 452.2, times the natural log of 0.444. And that's going to give us a delta G number. Now, the delta G number we initially have will be in joules per mole. And we need to convert that into kilojoules per mole. So we'll divide that number by 1,000 to get the actual desired kilojoules, which makes sense for our answers. So if you do all that, that comes out to be positive 3.05 kilojoules per mole. And again, to make sense of this, remember that K's less than 1, i.e. 0.444, those mean reactant favored. And reactant favored corresponds to a non-spontaneous delta G, a positive number. So K's less than 1 and positive delta G's absolutely go together. Answer D wouldn't make sense. A negative delta G would be corresponding to a K value much greater than 1, and that's not what we have here. So anyway, these are just things to do, but watch the kilojoules to joules things on these. That's the only tricky part that I can think of. Otherwise, it's pretty good to go. Okay, so that's the end of chapter 13, and I sure appreciate you being here and spending your time with me. There are more resources to help you learn the material. There's a study guide, which is basically a bulleted list of highlights. There's concept guides that show you worked answers, how to go from the question to the answers. I also have equilibrium constants handout. We're going to be seeing lots of types of equilibrium constants, not only this chapter, but in future chapters. This chapter, we've talked about Kc and Kp. There will be other types of K coming in, so that might help you along the way. And you can look at the other things as well. Thank you for spending your time with me. I know you have other things to do, and I do appreciate it. And if you have any questions, reach out to me. I'm more than happy to help. All right, good luck with your studying, and have a great day.